Good afternoon, everyone. My name is Chang Liu from Osaka University, Japan, and today I'll be talking about our study, which is titled Intellipupil, pupillometric light modulation of optical C-through-head-1 displays. So, as most of you may know, the optical C-through HMDs can display virtual content directly in the user's field of view. So, because of this, it has very good capability for providing AR experience. And from our point of view, we think that a good optical see-through HMD should be ideally hands-free and be flexible to any change of the environment. But unfortunately, we still have many issues to deal with. And the main issue here we are dealing with in this study is the visibility issue, which is caused by the mismatched lighting between the display and the real world. So for example, if we have a very dim display compared to the real world, then the user will not be able to recognize the virtual content on the display. And if the display is too bright, then the user will lose the sight of the real world, which is kind of dangerous, especially when you are rendering some content in a wide field of view, well, hopefully someday. So so it's about one single frame, but think about the practical use of the HMD. Even if we are staying in a very common indoor situation, and there will be for example, near the light, there will be a very bright areas, or there will be very dark areas in the user's field of view. So the real world is very complex about the brightness, and also the user will constantly move their head when they do something with the HMD. So the dynamic head movement will also influence the visibility of the HMD if you keep the content at the same brightness. So, the best solution is to ask the user to adjust it to their preferred brightness, but unfortunately it's not so user-friendly to ask a user to adjust it continuously. So we need a kind of automatic adjustment of the brightness to let the display be flexible to the change of the environment. And actually, back in 2010, the team of Yamazoe, they did a user experiment to figure out how the brightness adjustment will be effective to the improvement of the visibility. And you can see from the left side, and they have 3 monitors, normal monitors as a background, and they set it to 4 different levels and let the user change the display brightness to their preferred level. So they concluded that first, the backlight control will be effective in improving the visibility of the display, which is not so surprising. And besides, they found that there is a huge individual difference between the preference of the HMD brightness. For example, some user will prefer brighter display, while some other user will prefer dimmer display. So it is, they said that, so in their experiment, they only used a simple linear adjustment, which is based on the environment brightness, and they said that we need to seek for a optimized adjustment, which is based on the user evaluation. So think deeper about the limitation of the linear adjustment. First of all, it doesn't take the user's preference on the brightness into account. And if you are going to use a camera or a sensor to measure the brightness, measure the light going into the user's eye, then it's not so accurate because first, the sensor will have different field of view with the user's eye, and also it cannot detect the user's eyeball movement, so the measurement will be quite different. So to us, we think it's important to find another reliable element which can measure how much light is passing onto the user's retina, really. So the initial hypothesis behind our study is that we think the user's pupil response would be effective for the light modulation because the pupil response is part of a light adaptation of the human body, and it's controlling its size to restrict to control the perceiving light of the eye. So if we can make use of the pupil response, then we'll be able to estimate the light that is passing through onto the user's retina, which will result in the effective adjustment for the brightness of the HMD. So the basic method is that assume we have a perfect situation where the HMD, the brightness of the HMD matches the environment and the user's preference perfectly. So if we can take the HMD brightness and the environment brightness as the input, then we will get a user-preferred contrast mapping. And also the brightness of the HMD and the environment with the user's pupil size will give us the information about the light adaptation mapping of the user. So if we can make use of these two maps properly, then hopefully we can get a method which is based on the user's preference and the user's light adaptation. But unfortunately, it's very hard to build a model to fit these three parameters mathematically, because the pupil size will change it's very sensitive to many elements. So because of this, we took another straightforward solution, which is to use a neural network to train a model which can reproduce the user's preference based on the brightness of the HMD and the brightness of the environment. So our system works like, our system have two phases. So in the first phases, which is the training phase, we take all these three parameters as the input to a feedforward neural network, so that we'll get a reproduction model to reproduce the user's preference of the brightness. And then when we are doing the auto adjusting, we only take the environment brightness and the user's pupil response, so that we send it to the reproduction model, and so that we can get a optimal HMD brightness, which is based on the reproduction model. So based on this method, we implemented a prototype system and did a user experiment. So in this system, we used a HoloLens with a single eye tracker on the left side, and we used a high dynamic range luminosity sensor to take the brightness of the environment. And the eye tracker is a normal infrared camera. And also, we normalized the brightness of the HMD from 0 to 1, so that we can adjust the brightness more smoothly. And we had, as a result, so we had 9 subjects in this experiment. Actually, we tried to hire more than 10 subjects, but some of them is not. So the eye tracking didn't work on some of them. So at last we got 9 subjects in total. And this experiment contains 2 phases. First is the training phase, which is the data acquisition for training the model. And on the second phase, we set up some simple tasks to compare our adjustment method with a single linear method to see if the pupil-based adjustment will work. And first, let me introduce about the training environment. So we trained this model in an indoor environment with 2 lighting conditions. So the first one is we left all the light on in the room, and of course the curtains on, so that we will get a relatively bright environment, indoor environment. And another one is we left all the light off, so that we will get this kind of relatively dark environment. And also for the virtual content on the and user will look through the HMD and in these 10 directions, and they chose their preferred brightness. So that we'll get the training data for both of the two HMD content. And we let them to choose their preferred brightness for 5 times so that we'll get a more smooth result. And first, let me show you the matching result of the neural network. It's a very quite simple neural network which only have 2 hidden layers. And so from the result we can see, so the result with high matching high fitting rate is marked in red, and we can, well, basically it has a very good fitting rate. And if we show the best matching result in the figure, we can see that the user's preference for the brightness is not so linear, and even for the best matchings, the shape are quite different. So which And for the evaluation phase, the task is that this time the user, we don't use the marker. So the user is, the participant was asked to gaze at a random direction for any part of the room. And this time they rate, so the brightness of the display is automatically adjusted. So this time they have to rate how close the brightness is to their actual preference. And they voted it in a 7-level Likert scale score. So the result for this evaluation is like this. So note that if the score 1 means the HMD is too dim, and the score 7 means the HMD is too bright. So score in the middle, the 4 is like it's my best preference of brightness. So if you check this result, you can see that basically our method outperformed the linear-based one, which is not so surprising because the linear adjustment is just, it doesn't account for the user's preference. So so first, from the experiment, we can see that the Intellipupil, so our method outperformed the linear adjustment on matching user's preference on the brightness, but still it's different. It's somehow different from what the user is really preferring. And so what we can say from this result is that first we need more training data, because we tried to constrain the whole experiment into 1 hour, so we cannot collect too much data for every participant. And maybe there are still there should be another unknown parameters that could influence the performance of the model, such as like the lit pixels of the content and the real-world color on the background, and maybe for the pupil size, maybe the user's mental state or something like that. So for the future work of this study, first we want to dig deeper into the pupil response when they are using optical see-through HMDs. And also we want to integrate our system with the eye gaze tracking and the scene analysis so that we can get a more accurate model, or a model that is more precise to all the information. And also this time we did the user experiment in an indoor environment, but actually an outdoor environment has much higher dynamic range. So hopefully we can design an outdoor experiment to try to test our performance. And that's all of my presentation. Thank you for attention.
So future display has to be smart in a very different way. So any questions from the audiences? Then maybe I just start the Q&A. So your system, do you think it's also helpful to use the gaze information? Like for example, if I look at the scene, these lights are more brighter than the others if I look directly into it.
Yes, so that's what we are going to actually, and so the eye gaze with the scene analysis could give us like more information about what the user is looking at and what object, what like depth the user is looking at. So if we can use that kind of parameters, and then well, definitely it will improve the performance of the vernier adjustment actually on the HMD. But for this study, and what we focused on is that if the pupil response can be used for this adjustment, so we try to like avoid all the other parameters. But yeah, definitely we will do that in the future.
Any other questions? Because we still have plenty of time. Otherwise, yeah.
Hello, thanks for the talk. My question is, does your system already somehow recognize the discrepancies between the brightness that the HMD recognizes and possible the pupil reaction? So you said you trained your system in different scenarios, but then you use it live and you look at a really bright scenario, but the pupils are not pulling together. So medical issues or health issues or something, does your system already recognize that?
Actually, no. So in this study, we only concerned the brightness and the pupil size. So we didn't care about like how if they are healthy or if they feel good today. So, well, which is actually quite hard to like quantitatively how can I say describe. So yeah, so in this study we didn't account for that, but yeah, there may be some possibility that the pupil size changed because of some like mental problem, something like that. So thank you for your comment.
Okay, then maybe one more last question. Okay, otherwise let's thank the speaker.